All right, day 4 is going to be talking about trapezoids and kites. These are quadrilaterals, but they're different from the ones that we were talking about on day 2 and day 3. Day 2, we talked about parallelograms in general, and we kind of introduced that idea. And then day 3, we talked about special types of parallelograms, your rectangle, your square, and your rhombus. Today we're going to be talking about trapezoid and kite. So these are not parallelograms. They are quadrilaterals, but they're not parallelograms. So there are different types of shapes that have their own unique details and properties that we're going to solve with. We don't have proofs today, but we do have a couple of different details and theorems we're going to be working with to see how these are a little more abstract and they work differently than the parallelograms. So first of all, our trapezoid, we're going to go ahead and define that. So a trapezoid is a quadrilateral with one pair of parallel sides. All right, put the 1 in all caps because that's important for how we define the trapezoid. So this four-sided figure only has one pair of parallel sides, not two. So remember, our parallelogram had both sets of opposite sides being parallel. This is not happening here. Only one set of opposite sides are going to be parallel. So that's what is the most distinctive difference between a parallelogram and a trapezoid. So this is an example of a trapezoid. They come in all sorts of different forms, but this is our generic representation here. So if you go ahead and put this here, right, we have our one set of parallel sides, and the other two would not be parallel. So this is kind of what your trapezoid will look like. Now, we have a couple of details that involve vocabulary I want to make sure you guys are aware of for the trapezoid. So with this here, the parallel sides are called bases. So we have a special vocabulary word for these sides that are parallel. We call them bases. So we're going to have two bases for a trapezoid. Okay, so the parallel sides in your trapezoid, those are called bases. The non-parallel sides we call those the legs. All right, so it look like this. All right, so the bases, these are important because you're going to hear in questions when they're talking about trapezoids, they're going to reference the bases and the legs, so you need to know what they're talking about. So the parallel sides in your trapezoid are the bases, and the other two sides that are not parallel, those are the legs. We also have two pairs of base angles. All right, we've heard of base angles before with the isosceles triangles. So base angles are really just angles that are along the base of something. So because these have two bases, the base angles would be here and here, right? We would call those two base angles because they're along this base. We could also call these two, I'm using different markings just to show that they're not necessarily equal, but you could, again, they're not necessarily equal to each other either, but these, we would call those two base angles as well. Now I'm trying to be careful to show that they're not equal because they are not always going to be equal in a trapezoid. In some trapezoids, the base angles would be equal, but not always. But you can still call them base angles. So don't let that fool you mixing up with the base angles we've heard before in isosceles triangles. And now that we're using them here, don't think that just because they're called base angles that they're automatically going to be congruent, because that's not always true for a trapezoid. All right, so this is just your generic trapezoid kind of introduction here. We have something else that's important to know in a trapezoid. We've talked about midpoint, and we've talked about mid-segment in a triangle. We also have a mid-segment or a median in a trapezoid, and it works almost the exact same way as a mid-segment in a triangle. So let's take a look at this little section here. All right, so the trapezoid mid-segment or median theorem states that the mid-segment, there I can spell. Mid-segment is parallel to the bases and is half sum of the lengths of the bases. Alright, so the midsegment itself, which I'm going to call M for midsegment, the midsegment itself in a trapezoid is going to be parallel to the bases. That's why these are parallel, right? And then we have the extra little arrow here to show this is parallel too. It's parallel to the bases and is half the sum of the lengths of the bases. So let's say I call this base 1 and base 2. Say I go ahead and label them that way. So this theorem is saying not only is this parallel to the two bases, which is incredibly important to remember, because they'll throw that at you when you're not expecting it, so do remember that the midsegment is parallel. But this theorem also goes on to say that the length of the midsegment is half the sum of the two bases. So this is a formula you guys are going to want to remember. It should look really familiar. It's just, just like our midsegment, or sorry, our midpoint idea is when you take two things, add them together, and divide by 2, right, the average. So that goes along here too with the midsegment of a trapezoid. So that's really important to remember here. Now also you guys want to make sure that when they're talking about midsegment, you remember, we talked about this for the triangle, remember that the midsegment by definition goes from the midpoint of one side to the midpoint of the other. That's why it's called a midsegment. It connects the two midpoints. So we've talked about midsegment before in a triangle, so I'm just reminding you that is the definition of a midsegment. So make sure you're looking for that in a question to confirm that it's actually a midsegment before you try to do this. So always make sure you're double checking your picture. You have all the information set up for you to use these properties. All right, so we're gonna, on the next page, we're gonna practice how we could use that potentially in a solving situation. But do you remember the midsegment formula as we're moving on? So this will work in any sort of trapezoid, which we introduced up there. Now I'm going to talk about a special type of trapezoid. So the isosceles trapezoid, a trapezoid, this is our definition, a trapezoid with congruent legs. Right, so it's still trapezoid, so we still have the whole parallel bases thing going on, but this is unique that the legs, the non-parallel sides, are going to be congruent. So it's just like an isosceles triangle, right? In an isosceles triangle, the two legs are congruent, and same thing here with the trapezoid, the two legs are congruent. So when you guys have this kind of situation, we actually have a couple of things that we can use to help us solve. And a run-of-the-mill trapezoid, just a generic one, there isn't a whole lot that we can do with that, because again, like I told you, the base angles are not always equal in a just generic trapezoid. So there's not a whole lot you can do to solve, to find like side lengths or angles or stuff like that, and unless it's a special type of trapezoid or it's labeled very distinctly. But for this one, we have a lot more that we can actually work off of. So some things to remember about this: the base angles are congruent. So this goes along with the isosceles triangle idea. When we had the base angles theorem for the isosceles triangle, we knew that the base angles were congruent, and so that's also going to work here. Your trapezoid will have congruent base angles as long as it is isosceles. Okay? If these two legs are not equal, you are not guaranteed to have that these base angles are congruent. You have to have the isosceles property first before you can say that the base angles are equal. Okay? We also have the diagonals are congruent. That means full diagonal, by the way. So if you were to draw the diagonals, and I'll pick a different color, if you're going to draw this diagonal, that is equal to that diagonal. So the full lengths are equal to each other. So from this corner to that corner is equal to the distance from this corner to that corner. Right, so that's the second property that you guys can know about isosceles trapezoids. Diagonals are congruent. And then lastly, consecutive angles are supplementary. Now this is not, this is not unique to an isosceles trapezoid. It's just something I want to make sure I mentioned. All right, because in any trapezoid, these are parallel, and this is a trapezoid. So in any trapezoid, these two angles right here would be supplementary. I'm just bringing it up here since we had more information to go along with the isosceles trapezoid. It felt like a good place to put that property right here. But for any trapezoid, because every trapezoid has those parallel lines and transversals the leg is a transversal. Any of these consecutive angles are going to be supplementary. All right, so just remember that in case you need it, because they could say like, hey, this angle is 80. What is this angle? And you have to remember, oh, parallel lines, they're consecutive interior, they're supplementary, so that would be, I think 80, so that would be 100, right? So that's just something to remember with the trapezoid as well. You do still have those parallel lines. All right, so that's a trapezoid. That's really all you guys need to know about a trapezoid. Your generic trapezoid, your isosceles trapezoid that has more you can work with, and then your mid-segment formula within a trapezoid there too. All right, moving on to the kite. We're going to talk about the kite, and then we'll practice with some application questions for either of those two shapes. So a kite here, here's a definition for a kite. A quadrilateral, I always forget how to write this out, with two distinct pairs of adjacent sides that are congruent, or congruent sides. It's a little bit wordy, but whatever. All right, so a quadrilateral with two distinct pairs of adjacent sides that are congruent. Now the word distinct is important to understand how this works out. I'm sure you guys know what a kite is, like the flying in the sky kite. That's kind of where this shape comes from, right? You understand the shape by understanding that visual in your head of what a kite is. So what this is saying is that with the two distinct pairs of adjacent congruent sides, basically they're saying that these two, like the upper half of the kite, these two are equal, and then the lower half of the kite is equal, but the distinct part means that these are separate. Like these two are equal and these two are equal, but you can't say that these two are. And that will always be the case for a kite. The reason why they have that is because if you have this kind of situation, which I'm going to draw very poorly, if you have this, right, that's no longer a kite, that's a rhombus, okay? So they have to say that the relationship between these two being congruent and these two being congruent, they're separate from each other to get that elongated kind of shape here, because if they were equal to each other here and here, but also up and down, then that would be a rhombus, not a kite. So we kind of rule that out with that word distinct. So this is our definition of a kite. This is what it's going to look like. There are a lot of different things that you guys can get with a kite, and I have a color coding strategy that I want you guys to use. I hope I have enough colors in this pen. But there's a really cool color coding strategy you can use to help understand what's congruent within this shape to make it easier to solve. So a couple of things to know about the kite. The diagonals are perpendicular, as you can see in the diagram. The diagonal is perpendicular, so right here, right, you have that 90-degree angle. It's true for all four of those angles if you want to draw them all in, but those diagonals are going to be perpendicular. Now, you should notice that there's a longer diagonal and a shorter one, so we call the longer diagonal here, we call that the major diagonal, because it's longer, and we call the shorter one here the minor diagonal, because it's shorter. So these next two things, I'm going to be using those two words, the major and the minor, just so you guys can understand what I'm talking about. So property 2, the major diagonal bisects the minor diagonal. And I'm abbreviating because I don't have a lot of right there. So what this is saying is that this major diagonal, when it slices past or through the minor diagonal, it actually cuts it into two equal parts, that bisect idea. So this diagonal is being cut in half, but obviously you can see that the longer one is not. So they don't bisect each other, it's just that the major diagonal cuts the minor diagonal in half. So please make sure you keep that straight in your mind. It's not that they cut each other in half, it's just the one. The shorter one's being cut in half. And then our last one here, the major diagonal bisects opposite angles. So the major diagonal is going to bisect the opposite angles. Now this is where I want you guys to get your colors out so you can do some color coding. I'm going to color code all of the angles, or all the angle pairs figures that are equal to each other, and you'll get to see how that will help you solve in a second. So this whole major diagonal bisecting opposite angles thing means that this diagonal, this angle right here is going to be cut in half. So I can say that this is equal to this. Right, so that's one color. I hope I have enough. All right, not only does it bisect this angle, it bisects the one that's opposite that. So it also bisects this full angle right here. So I can say that this is equal to this. Right, so that's taking property number 3 and putting it into this picture in color format. So these two are equal and those two are equal. Now, look a little bit closer at the diagram. If you guys notice how the minor diagonal kind of splits the kite in half, since these two sides are equal, you should notice that this is an isosceles triangle right here. And hopefully you guys remember isosceles triangles. If you have two congruent sides, those legs, then the base angles are going to be congruent too. So if you guys pick a different color, pink, then you can say that this angle is equal to this angle using that isosceles triangle in the upper half of the kite. You can do the exact same thing. You can invert it and see that the bottom half of the kite is also an isosceles triangle because these two sides are equal. So that means that those two angles right there, green, these two angles right here, I hope you guys can see this color, it's a little bit bright. But those two angles would also be congruent using the isosceles triangle. So you guys can see how the angles are equal in this picture. And if you just always color code your kite, once you get the picture and you're working on a kite, if you just color code really quickly, those two, those two, those two, and those two, when you guys are solving, it'll make it a lot easier to see, oh, those are equal, so I can put this number here. And it just makes the process of solving with a kite a lot easier. So you have those angles are equal, you can see those sides are equal, these sides are equal, and those two parts of the minor diagonal are equal. So you have a lot of stuff that's equal in this picture. The only things that are not equal is the segment and the segment, basically. So go ahead and keep track of those relationships and it'll make solving a lot easier. All right, we're going to go ahead and jump into some example questions, starting with an isosceles trapezoid. All right. All right, so given, we know that ABCD over here is an isosceles trapezoid, so I'm going to go ahead and put these markings in, since they've told me that. I know that the bases are parallel and the legs are equal. I know that angle DAB, the measure of DAB, which is this full angle right here, is 130. I know that AC, which is this, let me use colors, this full diagonal right here is 10. Draw a little arrow. I know that AD right here is 5, and then I know the slope of AB is negative 1/3. So then I'm going to use that information I have in the picture to go ahead and answer the questions here. So the first one, they want me to find out the length of BC. So BC is over here. It's the other leg of the isosceles trapezoid. And remember, because it's isosceles, it means that they're equal. So if I know AD is 5, that means BC is also 5. The legs are equal. So that's just using the definition of isosceles trapezoid. They also want to know BD. So BD is the other diagonal. And again, another property that you guys need to remember about isosceles trapezoids is that the diagonals are congruent. So they give me one diagonal, AC was 10, so that means the other diagonal is also 10. Pretty straightforward. They want me to find angle ADC, which is this full angle right here, ADC. So remember, trapezoids, no matter whether it's isosceles or not, these are parallel, and this is a transversal, so that makes these consecutive interior angle supplementary. So if they've already told me that that one is 130, that means that this one has to be 50 to be the supplement of that angle. Okay, so hopefully that came pretty quickly. And then I am also looking for a BCD, which is right here. Because this is an isosceles trapezoid, this wouldn't work for just any old trapezoid, but because it is isosceles, the base angles are equal. So since I found that one was 50, this is also 50. And then lastly, the slope of DC, which is right here. These are the two bases. Remember, the bases are parallel. So if the upper base has a slope of negative 1/3, this has to have the same slope in order to be parallel. So negative 1/3 as well. So that was pretty simple stuff. All right, now we're going to work with the mid-segment, all right? So it says solve for each variable, the legs are bisected. So they made sure to give you this information so that you can confirm that this is a mid-segment. If they just randomly drew something here and didn't tell you it was a mid-segment, I'd be really careful not to make assumptions. But they told you that the legs are bisected, so you can be like, haha, it's a mid-segment. So remember, when it's a mid-segment, just like a midpoint, you're going to do the average of what it's between, basically. So the mid-segment formula says mid-segment's equal to half the sum of the two bases. So this is base 1, this is base 2. I'm going to add those together. And I know you guys can do that. All right, so when you add those two together and then divide by 2, you get 19. So the mid-segment, the length of that is just 19. Okay? Same thing over here. Now this is different. They gave me the bases as values up front and just wanted the mid-segment. This is still using the mid-segment. They just made it a little bit more complicated because they have expressions with x for two different parts of the diagram, not just the mid-segment. So I'm going to use the same idea though. This is the mid-segment right here. Okay? The mid-segment is still equal to half the sum of the bases. Now I like the way that they drew this picture because I don't want you guys to get into the habit of thinking that the bases are always the bottom and the top. That's a common mistake that people will make. So this is not a base and this is not a base. All right, it's not always the bottom and the top. Remember, the bases are the sides that are the parallel ones. So they kind of twisted the trapezoid to kind of make sure you're okay with seeing the trapezoid in different orientations. It's these two are the bases because those are the parallel ones. So please make sure you're watching out for that. All right. So for this one, I'm going to go ahead and I'm going to multiply the 1/2 over just to make that a little bit simpler, and then 2x plus 42. All right, x equals 7. So it's the mid-segment question again, just slightly more complicated. So make sure you guys are okay with working with the mid-segment. All right, now we're going to see a kite. So remember, when you guys see a kite question, I strongly recommend that you guys just go straight for that color coding, like I was showing you with the angles, because it'll make accessing the information a lot easier. So I'm going to just really quickly do that. I don't remember where I put what color, so I'm just going to put them wherever I want really quickly. It doesn't matter which colors you use as long as you have the correct relationships. Those two are equal through the isosceles, and then these two are equal because of the isosceles. Okay, so those little dots, the colored dots, are all equal to each other. So now that I have that, you can also add in the little side markings like this. And now I have all the relationships that I need to know about congruency. All right, so the first angle that I'm looking for is KIE. KIE. So that's this pink one over here, that pink one right there. So if you notice, like when you have a kite, it's split into 4 triangles. Hopefully you guys can see that really easily. So I'm actually, as I'm solving for angles, I'm going to focus on triangles that are more relevant to the information I have. So some information you guys want to make sure you also include here that I didn't before is that the diagonals are perpendicular. So that gives me a 90-degree angle on each one of these 4 triangles, so that's going to help me on this one right here. I'm going to draw that over here, just so you guys can see what triangle I'm working with. I'm working with this upper right-hand triangle where I have the 25 and then the 90-degree angle, and then that's the angle I'm looking for. This little pink dot that I drew, I'm going to represent it with an X over here. Okay, so I'm using the upper right corner of that kite. So very straightforward triangle sum theorem. If you add the 90 and the 25 together and then subtract that from 180, that means that X is 65. So this angle right here is 65. That might come in handy, so I like putting it over there so I can access the information easily. All right, angle KIT. KIT, so that's this full angle. It's both the purple and the green put together. So for this one, instead of looking at a, well, not a fourth, but instead of looking at the upper part of the kite, I'm actually going to look at it as 2 triangles. I'm going to look at split down the middle and then up like this, so like this, that part of it, kind of ignoring that extra part of the minor diagonal. That's the triangle I'm going to focus on. Because if I know that this is 25, and I notice that this full angle is 30, but it's been bisected, so that means this is 15, each of those little sections is 15, that leaves this as what I'm looking for. That's KIT is right here. Okay, so that's the triangle I'm going to work on. I'm going to draw a little sketch again, right? I know this is 25. If I bisect this full angle, that means this is 15, which is real small. And then the X is that angle right there. So again, triangle sum theorem, just using half the kite instead of the upper corner. If you do triangle sum theorem, you get 140. Again, add the 25, 15, that's 40, subtract that away, you get 140. Okay? So again, in kites, you are often breaking it down to triangles like we've done before with the other shapes, like rectangles and squares and stuff. So make sure you're using your triangles to your advantage to help you see the information. All right, MET. MET, that's this green one right here. So I'm looking for this green angle. So what I'm going to do is I'm actually going to use this bottom left section, which is this triangle. I like to draw little, you don't have to, but I like to draw little sections over here so I can see what part of the kite I'm focusing on. So I'm trying to find MET, which is this little section, this little X, and just in the previous question, I just determined that this full angle 30 was cut in half, so each of these is 15. So that little corner is 15. So I have 90 and 15, so again, triangle sum theorem, that's going to give me 75 for this one. Okay, I'm going to go up here and finish with the angles before I move into the segments. So I'm going to come up here to EMK. So EMK, so that's this angle right here, and that's using the definition of the kite, or not definition, but property of the kite, says that those are perpendicular diagonals, so that means that that's going to be 90. And then our last angle, EKT. So EKT is right here, this is the blue one, right? So I said these two angles are equal because I already know one was 25, that means this is 25, right? So some of them are easier, some of them are harder, just depends on what you're looking at, so be careful to understand how to navigate through that picture. All right, I'm going to transition into the segments because you can find segments with kites just in a slightly different way. Still using triangles though, interestingly. So KE is right here, that's along here. So I'm actually going to use the definition of kite to help me with this one. So I know this and this, they have to be equal. All right, and they told me that was 5. So that means that KE also has to be 5. If I come down to MI is this little segment of the minor diagonal. Now I don't know what the full length of the minor diagonal is, otherwise I would just cut it in half. But what I do know is that MI is a part of this upper triangle, the one that has a 4 and a 5 in it. Okay, so I'm going to draw that triangle. Don't want to confuse it with this picture, but all right. So I have the upper right corner of the kite. I know that this is 4, I know this is 5, and ME is this one right here, the X. Okay. So what's interesting is that with this little right angle here, that's a right triangle, like we were saying before when we were using it up here. But I'm going to switch to solving for sides in a right triangle. Hopefully you guys can see immediately. I know 2 sides looking for a third. That's Pythagorean theorem. Hopefully you guys should see that very quickly. If not, just make sure you guys are remembering our Unit 7 and when you're given certain information in a right triangle, how to recognize what strategy to use. But this one is going to be Pythagorean theorem. It's actually a Pythagorean triple. If you notice that too, then that's really awesome. So the hypotenuse is 5, one of the legs is 4. That means this one has to be 3 for a 3, 4, 5 Pythagorean triple. If you don't remember that, it's okay. You can still use Pythagorean theorem. X squared plus 4 squared equals 5 squared. Solve it out. You'll get that x is equal to 3 either way. Okay, so that one worked nicely for us to get that value. All right, EM. So EM is right here. EM is the other half of the minor diagonal. So now that I found this half, the MI, I know that these are equal by that property of kites. So I can say that EM is also going to be 3. That one was nice and simple for us. Now I'm going to look at ET. ET is this side right here. So I just recently found, just a couple seconds ago, that both of those are 3, right? So sometimes the questions moving down through a set of problems requires information from the previous question. So again, it's good to keep track of what you know and put it into the picture. So I'm looking for ET, which is this side in the bottom left triangle. Running out of room to draw these, so I'm actually going to draw it over here. Okay, I just found that this was 3. I already know in the picture that this is 10, and I'm looking for ET, which is represented by X right here. So again, it's a right triangle. I know 2 sides, looking for the third. It's Pythagorean theorem again. This is not a Pythagorean triple, though, so you guys will have to write out the work. Oops. 3 squared plus 10 squared equals X squared. That's 109, right? 109 as a radical, when you take the square root, it can't be simplified. So this one right here is just going to stay as the square root of 109. Remember, never give me decimals. When you're working with square roots, just give me a simplified radical. This one can't be simplified, so it's just square root of 109. And then over here, our last one is IT, And because the definition of a kite says that these two adjacent sides, those are going to be, not adjacent, sorry, these two sides right here, well, yeah, I guess they are adjacent. Sorry, sidetracked. Those are going to be congruent. We already put the little congruent markings right there. So if I already did all the work over here, you don't have to do the whole problem again. If you already know that this is square root of 1 and 9, you can just write square root of 1 and 9 over here too, because you know that they're equal, right? So yes, some questions for a kite are more tricky than others. Sometimes they involve more work. Sometimes you have 45, 45, 90 and 30, 60, 90 triangles within a kite, so you have to remember those rules too. Anything from chapter 7 with the right triangles could come back, well, not necessarily trig, but the other solving, like the special right triangles and Pythagorean theorem, they may come back with kites because they have the right triangles in there, so just make sure you guys are careful and looking out for those situations. All right, just a couple more to practice, a little bit more with trapezoids in a different context. So these two questions are word problems. See if you guys can figure out how to approach these. So this one says an isosceles trapezoid has legs that measure 24 units each. So they're equal, so I got 24 and 24. If the perimeter of the trapezoid is 150 units, what is the length of its median? So median is another name for midsegment. So I'm going to go ahead and draw that here and put an M for midsegment or median. Now they told me the perimeter all the way around is 150. So remember the formula for midsegment involves knowing what the bases added together would be, and they didn't tell me what the bases were. But that's okay. We're actually going to be able to still solve for the median, even though they haven't specifically told us what base 1 and base 2 are separately. So take a look. What we're going to do with this one is we're going to work with the perimeter idea first. So I'm going to call this base 1 and base 2, like we did in the theorem. So the perimeter is all the sides added together. So it should be base 1 plus base 2 plus the two 24s, the two legs added together, that's 48. So this is your expression for the perimeter. The perimeter is all the sides added together. What's interesting is that when you guys subtract the 48 over here, sorry, you get 102 equals B1 plus B2. Excuse me. What's cool here is that, remember, the midsegment formula looks like this. It's M equals 1/2 times base 1 plus base 2. I don't even need to know what base 1 and base 2 are separately, because I found out what they are together. So if you don't know what they are separately, but you do know what they are together, it doesn't matter what their values are, because now to find the midsegment, you can just plug in the 102. We know what they are added together, which is really all we need for the midsegment formula. We don't need to know what they are separately. So that's actually an interesting to know them separately. We're just able to use the sum because we knew what that was from the perimeter. So when you guys go ahead and work through that, half of that's 51, right? So that would be the measure of the midsegment. Cool. All right, so our next one here, the trapezoid has bases D, G, and EF. So those are our bases. That means that they are parallel. Okay. DG right here is 12 and EF is 18. The perimeter of the trapezoid is 48. What is the length of FG? So they've told us what the bases are. Notice these little markings here. They're saying that the two legs are equal. So this is an isosceles trapezoid. I'm actually going to put an X here and here. I know we're just looking for FG, but because these are both equal, I'm going to put an X in both of those positions. Because again, they've given us the perimeter, and the perimeter requires something on all sides of the polygon here. So I'm going to go ahead and use that perimeter, the 48. So 48 is equal to 12 plus x plus 18 plus another x, right? Just add all the sides together. And so x represents the length of FG, so all I have to do is solve for x. So this is actually pretty basic algebra. I think it's just one, nope, just kidding. That's 30, so that's 18 equals 2x. X is equal to 9. There you go. So again, just using the perimeter idea and the fact that this one was isosceles. Worked with it differently because this was looking for midsegment. This was just looking for what the length of the leg was. That was simpler. All right, so there's a little bit more practice with trapezoids. Here's even more practice with trapezoids. Yay, practice. All right, find the angle measures of ABCD. So they basically just want you to find the angles that we don't know, so all the blank ones, boom, boom, boom. All right, so we know it is a trapezoid. We also know it is isosceles because of these little markings here. So this angle right here, because it's a base angle, these two are equal. Okay, isosceles trapezoid. We also know that because these are parallel, the consecutive interior angles are supplementary. So if this is 112, I can find the supplement of that, and that would be this angle. So what is that? That would be 68. All right, so mental math. Yep. And then again, because this is isosceles, or since you know this is 112, you can do consecutive, or just say that those base angles are equal to, but you'd have 68, 68, and 112. Over here, this is not isosceles. Again, that means that the base angles are not going to be equal because it's not isosceles, but you can still use the parallel lines to help you. So because these are parallel and this is a transversal, these have to be supplementary. So if this is 90, that makes this 90 as well. All right, so that's one of them. And then also, these two have to be supplementary as well. Again, they're consecutive interior, so that would be 48. Still checking, yep. So that was really straightforward, but just testing your understanding between the difference here. Again, you don't have congruent base angles here because it's not isosceles, but you do over here. So make sure you keep that straight in your brain. All right, how are we doing on time? I don't know. Okay, we're good. So for this one right here, we're going to practice with trapezoids. I know you guys tend to struggle with those sometimes, always, never questions, so I threw some of these in here just to stretch our brains a little bit more with our trapezoids. So these are prompts to have you guys try to draw these, and if it's not possible, we got to figure out why is it not possible to do that. So for this one, I want to see if you guys can try to draw a trapezoid with 2 right angles. So I know you guys are watching this without me here, so I'm just going to pause for like 10 seconds and see if you guys can figure it out, and then I'll show it. All right, so for this one, it says to try to draw a trapezoid that has 2 right angles. So this one actually is possible. So remember that you always want to start off with 2 parallels, right? You have to have the 2 bases for a trapezoid that are parallel. If you just draw this right here, right, and then extend this out a little bit and draw the angled side right there, you have 2 right angles right here, and that's a trapezoid. So that one's possible. That one's good. All right, see if you guys can draw a trapezoid with bases that are shorter than the legs. So this one is also possible. You just kind of have to stretch it out a lot to make this work. So let's say you had like a base here, and then your other base is just slightly longer. So you pull it down just a little bit so it's just slightly longer like this. And then you connect, right? Clearly, these 2 bases are shorter than those 2 legs. Okay, so you can do these. You just have to make it elongated to get it to be obvious how you can draw that one. All right, this one right here. I want to know if you guys can draw a trapezoid according to our definition that we wrote with congruent bases. So see if you guys can do that. This one is actually not possible. So I know you guys are probably thinking, well, I can do this, right? I can do that. They're parallel. They're congruent. Why can't I just do that? Okay. Well, think about our definition of trapezoid again. Our definition of trapezoid was that it was a quadrilateral with 1 pair of parallel sides. If you look at this right here, what you guys just drew was these 2 bases Remember, the bases for a trapezoid have to be parallel, so they're parallel, but they're also congruent. If you think back to day 2, when you saw a picture like this, where one pair of sides were both parallel and congruent, that was one of our tricks to show that something is actually a parallelogram. A trapezoid cannot be a parallelogram. You cannot have 2 pairs of parallel sides and it still be a trapezoid. So even though I physically have drawn one set that is parallel, if they're both parallel and congruent, that shows that it's a parallelogram. That's one of the things that we use to prove that something's a parallelogram. So what we just drew is a parallelogram, not a trapezoid. So this one is actually not possible, right? NP, not possible, all right? So if you want a quick explanation, if bases are parallel and congruent, that's a parallelogram, not a trapezoid. So that's just a brief explanation of why that would not work. So you really do have to weigh our definition and how specific it is with how you can only have one set of sides that are parallel, and how that kind of breaks down that situation. All right, so now I want you guys to try this one, a trapezoid with 3 acute angles. So this one, hopefully you guys have pretty quickly run into an issue here. So again, with a trapezoid, you do need to have your parallel bases, right? With this scenario, if we're trying to make the angles acute, if I try to make, let's say I make this a little bit longer, and I make this one acute, right? That automatically rules this one out as being acute because they have to be supplementary. So because by definition a trapezoid has to have these parallel sides, if you make one of them acute, the other one has to be obtuse to get that supplementary relationship. So this one's not possible. Okay, this one you can't do. Not possible. Rules out. Supplementary consecutive angles. Right? So that one's not going to work out for you so well. All right, now I want you guys to try the next one, a trapezoid with 3 congruent sides. Hopefully for this one, you guys are able to conclude that yes, you can. So for this one, if you have your base, you have your first base like this, and then you get your the two legs to match that length and then swing them out. So I can't draw it perfectly, but like if you draw it so it's like that, so your 2 legs and your 1 base are equal, they kind of swing out like that to make the other one a little bit longer. That's how you can draw a trapezoid with 3 congruent sides. Okay, so that was an interesting little brain teaser. And then we have just a couple more examples. I really want to make sure that I'm covering all our bases for the different types of questions you guys can see with these shapes. So this is random scattering of different types of questions, so sorry. It's a little bit random. So we just have a couple more. So this one is a kite. We were trying to find the lengths of the sides, so any of these that doesn't have a length already, that's what we're going to be finding. So that's going to be, so we already know everything on the inside basically, so we're just finding all the outside portions of the kite. So again, when you guys are looking for sides in a kite, it's almost always using either Pythagorean theorem or your 30, 60, 90, 45, 45, 90 rules, depending on what the angles are. But for this one, so I'm going to redraw this, right? All right, so I noticed that in the upper corner here, both of these are going to be equal. So once I find this side is going to be equal to that one. So I only have to do the question once to find both. So that's nice. 2 for 1. So for this one, you should notice that this is 12 and this is 12. So this is actually an isosceles right triangle. Now technically you could do Pythagorean theorem if you wanted to. You could do 12 squared plus 12 squared equals x squared and solve that way. But I hope that you guys notice that because these sides are equal, that means that the angles are equal. So this is actually really a 45, 45, 90 triangle. So when you guys recognize it's a 45, 45, 90 triangle, you don't have to do that whole scratch word process of the Pythagorean theorem. You can just remember what the rule is. Because they gave me the legs, right? Remember the hypotenuse is a leg times square root of 2. So once you notice it's 45, 45, 90, all you have to do is be like that, use the rule. It's the leg times square root of 2, so it's just 12 square root of 2. All right, so that bypasses the extra couple of seconds you'll use out doing Pythagorean theorem, but that's still valid if you'd like to. So this side right here is 12 square root of 2, and so is this one by the definition of your kite. Okay, same kind of thing. I'm going to redraw this triangle right here. This is 12, this is 20. Now this is not a 45, 45, 90 triangle because the two legs here are not the same, so I do have to use Pythagorean theorem, but that's okay. I think this is actually also a Pythagorean triple. It's 3, 4, 5 times, no, actually I don't think it is. No, it's not, just kidding. They're in the wrong places. So for this one, Pythagorean theorem, 12 squared plus 20 squared equals x squared. So that's 544, because this is 144 and 400, so you add them together. And then I'm going to take the square root. I don't think that can be simplified. Did I simplify it? Oh, yes, you can. It can be. Sorry, you can simplify that. So it's 16 times 34 according to what I see over here. But let me just double check that really quick. Yeah, 16 times 34. So when you simplify that, that just becomes 4 root 34. So these two sides right here are equal, so I just have to do the problem once. This is 4 root 34, and this is 4 root 34. So that's the whole question. So this one I like because it shows that instance of the 45, 45, 90 that you can use as a shortcut. In any situation, you can use Pythagorean theorem. But when you notice it's 45, 45, 90 or 30, 60, 90, if they were to give you those angles, it can be useful. Especially in a kite that looks like this. That is horrible. But if they were to give you like, I don't know, something like this, right? And these kites, they gave you every piece of the minor and major diagonals, but what if, here I'll give you a different side, what if they were asking for this, but they only gave you that? You can't use Pythagorean theorem on that, right? You need two sides in order to do Pythagorean theorem to find the third. So this is really where you're forced to use the 30, 60, 90 because this is the side opposite the 60-degree angle, so you have to use that rule. So just remember that that's always a possibility, but Pythagorean theorem can also work as long as you have the correct amount of information. All right, last questions here. All right, still kites, but these are diagonalless kites. They don't have their diagonals in them. So I'm going to be looking for the missing angles here. So angle A and T here, and then A and H right there. So this one's interesting. I like how they don't have the diagonals here, but we're kind of using them still. So that color coding thing that I was showing you, we're using that, but I'm not going to put the colors in. So you have to kind of imagine the diagonals, and if you want to draw them, you can, feel free. So if you imagine the diagonals in the kite, we're going to be using that thinking to help us. So if I know, so for instance, if I know that this angle right here is 81, remember that the major diagonal, which goes down the longer part of the kite, it cuts opposite angles in half. So if I know that this is 81, and I redraw the kite like this, if I know that this, there we go. If I know that this is 81 and it's cut in half, that means each of these is going to be half of 81. which is 40.5. Like this. Right, that could be helpful. If I do the same thing like this angle is not cut in half. That's important to remember. It's only the major diagonal that's going to slice the angle in half. Ooh, excuse me. But I can still do this, right? I can still add that minor diagonal here, and remember that there's a 90-degree angle there. That can actually help me find this little section right there, which can give me a little bit more momentum to move forward in this process. Now that's one way of doing it. I just looked over here. There's actually a faster way that I noticed. So remember in the color coding, and I wish I'd saved it, but I didn't. Remember in the color coding when I was doing this, right? I said that those two are equal and these two are equal, right? So if I know that these two are equal and those two are equal, you should notice that this is red and blue and this is red and blue. So the full angle over here is also equal to the full angle over here. So if I'm looking at this diagram, I can actually find angle A really quickly. If I know this angle, I know it's going to be the same thing as this one, 118. So with the minor diagonal in there, you can see that the little pieces up top are equal and on the bottom they're equal. But if you combine these two and combine those two, their combined angles are also congruent. That's something pretty cool you can use as well. All right, so I have that 118, and then I think a faster route, that it's still true that this is being bisected, but I think a faster route we can take here is now, because it's a quadrilateral and all of the angles inside of a quadrilateral add to 360. Now that I know 3 of them, I can find the 4th one by adding those and subtracting from 360, which is what I did over here. So if you add those and subtract from 360, that leaves 43 right here. Oops, there we go. So you can always use the stuff from day one. We were talking about interior, exterior angles if it applies. So it applied here that all the angles inside of a 4-sided figure add to 360. So I was able to find that one. Okay, so that's still valid, but this whole thing was not helpful in the grand scheme. You can still use that method, it just takes a little bit longer. And then this one over here, again, this is a kind of weird looking kite. They really stretch it out. But again, you can use the split down the middle like this. They've given us the angles along the major diagonal, so both of those are being bisected. So this guy right here and the up, I'm going to draw half of the kite off to the side just so it's easier to see, like this. All right, so if this full angle right here is 74, but the major diagonal cuts it in half, so this one is 37. Same thing over here, this is 27, but the major diagonal cuts it in half, so that's 13.5. So you should notice that angle A, which is one of the angles I'm looking for, is the 3rd angle in this triangle. So you can use triangle sum theorem to find that one, which is 129.5 when you do the triangle sum theorem. And again, using the same idea over here, because these two combined is equal to these two combined, those angles are equal. So if I know angle A, I also know angle H. So those are the exact same measure. So that one was interesting without its diagonals. You can always add the diagonals back in and see how they help you move forward in that question. I think I have some questions like that on the homework, so just be aware of how to work through those questions. All right, so that's your day 4.